Hey everyone, welcome to this explainer. Today, we are completely skipping the standard syllabus to plunge right into the incredibly high-stakes reality of space engineering. We're not just looking at dry theories here. No, we are exploring the exact framework that keeps multi-million-dollar missions alive in literally the harshest environment known to humanity. Take a look at this. This tiny piece of human ingenuity, it's a CubeSat, is floating in the absolute void right after being deployed from the International Space Station. I mean, you are looking at millions of dollars of hardware, countless hours of intense labor, and basically the highest stakes imaginable. All of it just suspended out there in the silent, deadly vacuum of low Earth orbit. So that brings us to the ultimate question we're going to answer today. How in the world do you manage a project when your hardware is 500 kilometers above the Earth, completely out of your physical reach? Well, it proves that systems engineering isn't just, paperwork, spreadsheets, and endless meetings. It's the literal lifeline for satellite survival. Because honestly, if you get the management wrong down here on Earth, your hardware just becomes really expensive orbital debris up there.
Let's jump right into Section 1, Meet Your Mission Commander.
You're going to be in incredibly expert hands with Dr. John Bay. He's not just an academic sitting in a tower. He is an active industry leader. With a PhD in aerospace engineering from the University of Sydney, he's currently the engineering lead for major missions like QAVA and Warthaw Seed. Plus, the guy's a serial entrepreneur. He co-founded companies like SpeakDraw and Deneb Space, and he was even the systems engineer for the Spooky 1 CubeSat. So he brings direct, real-world, crucible-level experience straight to the table. And what's truly unique here is his total dedication to your mission success. Even with a massive workload, juggling startups, satellite launches, and lecturing, he actually ensures he's available for consultations during regular working hours to help you master this stuff. He even makes special accommodations outside normal hours for postgraduates. It's a super rare level of access to an active mission commander. All right, moving right along to Section 2, Surviving the Space Environment. Now, the Spooky 1 mission, that's a masterclass in rapid success. Back in April 2019, it launched aboard the Antares rocket. Just a couple of months later, by June, it was deployed into orbit straight from the ISS Kibo module. And the result? It successfully generated entangled photons in orbit. This was a massive achievement. Basically, a tiny 3U CubeSat acting as the first quantum light source in space, which totally raised the technology readiness level for quantum communication globally. But you have to ask yourself, how do we actually get from complex, exploded hardware blueprints to a fully realized operational satellite floating high over the Earth? The gap between a clever paper design and a functional orbital asset is vast. It's like a giant puzzle, and bridging that gap is where the true engineering challenge really kicks in. We get there through rigorous management. Why? Because space is actively trying to destroy your hard work. Just look at this UAVA 1 mission. They experienced major communications blockouts shortly after deployment. On UAVA 2, the onboard primary SD card was completely fried by radiation in just 5 days. 5 days! But through smart redundancies born from great systems engineering, the whole narrative changes. Warthaw Seed 1 achieved 10 months of flawless operation testing multiple payloads. And despite that fried SD card, UAVA 2 actually executed an auto-recovery protocol. Literally, planning for failure is what saves the mission. QAVA 2 is just a perfect example of this resilience in action. Because the engineers planned for that exact worst-case scenario, the satellite automatically booted right into its backup system. This clever move let it completely bypass the radiation-damaged SD card, enabling it to continue its commissioning activities and, amazingly, exceed its 200-day expected lifespan in orbit. Which brings us to Section 3, the NASA Systems Engineering Framework. So the real secret here? It lies in systems thinking. This is a holistic, interdisciplinary approach that balances technical specs, budgets, and physical constraints to mitigate your risks. It ensures you aren't just looking at isolated parts, like focusing so hard on the solar panels that you totally forget about shielding the memory card. Instead, it forces you to prioritize the overall survival and performance of the entire system. By thinking in terms of the whole system and building in those crucial redundancies, satellites like CuAVA-2 can continuously deliver incredible global data, like this stunning space weather and radiation mapping. And let's be real, you only get this amazing data if the system actually survives up there. When you master this NASA-proven framework in the course, you aren't just reading dusty theories. You're learning from documented NASA failures and successes. You'll master the full life cycle, from the second a concept is sketched on a napkin all the way to mission closeout. This heavily enhances your career capabilities, basically making you an ideal candidate for leadership roles. And best of all, you are handed practical, real-world tools, decision matrices, and templates that reduce your risks and costs right at the start of the design process.
Okay, let's wrap things up with Section 4, Mastering the Mission Lifecycle.
Fair warning, this isn't just a casual read-through. This is rigorous mission prep. It demands a dedicated effort of 13 weeks and over 12 hours a week of your time. That kind of deep effort is required to ensure your knowledge is robust enough for high-stakes engineering. Remember, space absolutely does not grade on a curve. Think of this as your personal launch sequence to success. First, you'll ground yourself in the textbook to build a rock-solid foundation. Then, you'll join the Thursday mission briefings online to tackle critical topics and get into some really interactive Q&A. You'll stress test your understanding with weekly quizzes, and then lock it all in through rigorous assignment reporting. It's pretty much a perfect blend of independent study and interactive support. And your primary guide through this whole journey will be the actual NASA Systems Engineering Handbook itself, specifically Revision 2. You will literally be using the exact same manual that professionals use to build interplanetary spacecraft. How cool is that? And of course, this will be seamlessly supplemented by Dr. Bai's weekly lecture notes, which do a great job of distilling this really dense material down into practical, bite-sized insights.
So I'll leave you with this final thought to ponder. The void of space is waiting. It is unforgiving, it is flooded with radiation, and it is entirely indifferent to your hard work. Your engineering management skills, your ability to apply systems thinking, and your rigorous planning are literally the only thing standing between mission success and total, complete failure. So, are you ready to manage that lifeline? Thanks so much for joining me on this explainer, and I really hope this deeply structured look at space systems engineering management has sparked your curiosity to learn more.